The paper presents a groundbreaking approach called Feature-Topology Fusion-Based Experience Replay (FTF-ER) for continual graph learning. This innovative method aims to alleviate the catastrophic forgetting issue in graph neural networks (GNNs) by leveraging both feature and global topological information. The authors propose a highly complementary approach that incorporates both feature and global topological information, significantly enhancing the effectiveness of the sampled nodes. They introduce Hodge Potential Score (HPS) as a novel module to calculate the topological importance of nodes, providing more accurate global topological information compared to neighbor sampling. By excluding neighbor sampling, HPS reduces buffer storage costs for acquiring topological information and decreases training time. The proposed FTF-ER method achieves a significant improvement of 3.6% in AH and 7.1% in AF on the OGB-Arxiv dataset, demonstrating its superior performance in the class-incremental learning setting. Continual graph learning (CGL) faces the challenge of catastrophic forgetting, where models forget previously learned tasks when trained on new ones. To address this, a novel experience replay method called Feature-Topology Fusion-Based Experience Replay (FTF-ER) is proposed. This approach integrates feature and topological information to select impactful samples for experience replay, overcoming the limitations of existing methods that primarily rely on feature significance or topological relevance. Existing CGL methods are categorized into three classes: regularization methods, parametric isolation methods, and experience replay methods. The latter is further divided into two subclasses: feature-based and topology-based methods. However, these methods neglect comprehensive graph data, leading to suboptimal performance. The proposed FTF-ER method employs two theoretically grounded approaches to calculate node importance scores: gradient norm score (GRAND) for feature-level importance and Hodge Potential Score (HPS) for topological level importance. HPS utilizes Hodge decomposition on graphs (HDG) to establish a natural and computable node potential function, enabling a global ranking from pairwise comparison relationships among all nodes. The FTF-ER workflow involves calculating node importance scores using GRAND and HPS, normalizing the scores, and obtaining the aggregated importance by calculating the weighted average of the two scores. This approach improves the accuracy of node importance and enables the model to maintain classification performance across tasks. The contributions of this work include presenting FTF-ER, a novel framework that alleviates catastrophic forgetting in CGL by efficiently utilizing comprehensive graph data. The proposed method integrates feature-level and topological-level scores to represent node importance, introducing Hodge Potential Score (HPS) as a preprocessing module that captures global topological information without adding neighboring nodes to the buffer. The proposed FTF-ER method achieves state-of-the-art performance on accuracy and time efficiency in the class-incremental learning setting, with comparable buffer storage costs to topology-agnostic methods. This work also discusses related research in continual learning and CGL, highlighting the limitations of existing experience replay methods and the advantages of FTF-ER. The FTF-ER method has several key benefits, including improved accuracy, reduced catastrophic forgetting, and efficient utilization of comprehensive graph data. The proposed approach has potential applications in various fields, including computer vision, natural language processing, and graph-based recommendation systems. In continual graph learning, the catastrophic forgetting problem arises when a model forgets previously learned tasks after being trained on new tasks. To alleviate this issue, the proposed method, FTF-ER, combines feature and topological information of nodes. This approach utilizes global topological information without introducing extra nodes, reducing buffer storage overhead. Hodge decomposition, a mathematical tool, has been applied in various fields, including machine learning, robotics, and image processing, to analyze complex data structures, approximate incompressible flows, and create algorithms for agent control and stream function computation in graph-modeled environments. In the context of node classification, each node V in a graph G equals V, E, has a category label y_L element of y, where y is the label set and c is the number of classes. Graph neural networks, GNNs, are the mainstream solution for node classification problems. Continual graph node classification involves training a model on a sequence of disjoint tasks t equals t_1, t_2, t_k, where each task t_I comprises multiple non-overlapping classes y_I and c_I is the number of classes in task t_I. The goal of continual graph learning, CGL, is to achieve consistent high performance across all tasks in the sequence, addressing both current task performance and mitigating catastrophic forgetting problems for past tasks. There are two main settings of continual learning: task-incremental learning, task-IL, and class-incremental learning, class-IL, with the latter being more challenging. Experience replay, ER, is a technique used to retain the model's classification ability for past tasks. Traditional ER methods preserve a small number of training samples from past tasks and replay them during subsequent tasks training. The key to ER methods lies in designing a rational experience sample selection strategy. The proposed FTF-ER method addresses this challenge by leveraging Hodge potential scores to obtain global topological information, enabling more effective experience replay and alleviating catastrophic forgetting. In graph neural networks, node importance scoring is a crucial task that can be addressed by integrating feature information and topological information. To this end, we propose a novel method called FTF-ER, which calculates node importance scores using two components: gradient norm score, GRAND, for feature importance, and Hodge potential score, HPS, for topological importance. GRAND measures the importance of nodes at the feature level by calculating the contribution of each sample to minimizing the model's loss function during training. This is formalized as the sum of the differences in loss values between the original model parameters and the updated parameters after optimizing the sample, which represents the generalization ability of the selected sample. This definition is approximated by calculating the L2 norm of the model gradients. HPS, on the other hand, calculates the importance scores of nodes at the topological level using Hodge decomposition. This involves solving for the Hodge potential score using the graph Laplacian increment 0 and the Moore-Penrose inverse increment 0. The complete node importance score calculation process is illustrated in Figure 2. We also define the loss function for CGL, which combines the loss values of the original graph and the induced subgraph stored in the buffer B. The node set stored in B is used to select the most important nodes, and we propose a simple strategy for selecting the node set, letting GB equals G, V, B. The proposed FTF-ER method offers several advantages, including the ability to integrate feature and topological information, and the efficient calculation of node importance scores using GRAND and HPS. In contrast to previous topology-based ER methods, our approach addresses their limitations and provides a more comprehensive node importance scoring method. In continual graph learning, acquiring topological information is crucial for accurate node importance scoring. Existing methods rely on local topological information through neighboring node sampling, which has limitations. The Hodge Potential Score, HPS, method, proposed by the authors, utilizes global ranking derived by Hodge decomposition on graphs, HDG, to measure the global topological importance of nodes. This approach enables more accurate global topological information and eliminates the need for storing neighboring nodes. HPS calculates the Hodge potential score, aggregating information from all nodes in the graph. This score is computed as the minimum norm solution of an equation involving the graph Laplacian operator and inconsistent local rankings. By leveraging global ranking, HPS captures topological information beyond local neighborhoods, overcoming limitations of existing methods. To further enhance node importance scoring, the authors introduce a fusion method combining HPS with GRAND, a graph neural network-based method. The fusion method employs a weighted average approach to combine node importance scores from HPS and GRAND after min-max normalization. A hyperparameter, beta, adjusts the emphasis of sampling, with higher values emphasizing topological importance during sampling. The resulting mixed node importance scores can be utilized through two strategies: deterministic sampling or probabilistic sampling. This fusion approach leverages comprehensive graph data, providing a more accurate representation of node importance. HPS offers advantages in continual graph learning, including accurate global topological information and reduced buffer storage costs. The HPS method's calculation and fusion with GNN are detailed, highlighting key definitions related to HDG and the benefits of using HPS in continual graph learning. By providing a more accurate representation of global topological information, HPS has the potential to improve performance in graph learning tasks. The proposed FTF-ER strategy for continual graph learning (CGL) tasks is designed to select the most valuable nodes from a complete training dataset. It involves sampling nodes along with their induced subgraph and adding them to a buffer. The time complexity of this algorithm is O(n), similar to GNN, but significantly lower than SSM, which has a time complexity of O(n squared). The space complexity of the buffer in FTF-ER is also O(n), with a lower additional space complexity compared to SSM. In the experimental setup, 4 public graph node classification datasets are used, providing a wide coverage in terms of scale, content, and structure. These datasets are standardized to adapt to the majority of GNN backbones designed for undirected graphs. Evaluation metrics include average performance, AP, average forgetting, AF, and average accuracy, A, to quantify performance. Experimental results show that FTF-ER outperforms the current state-of-the-art method in the CGL field and performs similarly to the joint training method. It significantly outperforms other CGL methods under the class IL setting, with an improvement of 1% to 3.6% in terms of A and 2% to 7.1% in terms of AF compared to SSM. FTF-ER is compared with several baselines, including EWC, LWF, MOS, GEM, ERGNN, TWP, and SSM, on 3 mainstream GNN backbones: GCNs, GATs, and GENs. The results demonstrate the generalizability of the CGL methods and the effectiveness of FTF-ER in selecting the most valuable nodes for the CGL task. The experimental results are presented in Table 2, showing the performance of FTF-ER and other baselines on the 4 public datasets. 2 versions of FTF-ER are tested. One using deterministic sampling and the other using probability distribution sampling. The results indicate that FTF-ER with probability distribution sampling performs better than FTF-ER with deterministic sampling. Overall, the proposed FTF-ER method demonstrates its effectiveness in selecting the most valuable nodes for the CGL task, outperforming other state-of-the-art methods and showing its generalizability on different GNN backbones and datasets. The authors present a comprehensive evaluation of their proposed method, FTF-ER, for continual graph learning. They compare FTF-ER with various state-of-the-art methods, including fine-tuning, EWC, LWF, MOS, GEM, ERGNN, TWP, and SSM, on 4 datasets under the class-incremental learning setting. The results in Table 2 show that FTF-ER outperforms these methods, achieving an average accuracy of 94.6% and 93.9% for the deterministic and probabilistic versions, respectively. An ablation study is also provided to demonstrate the effectiveness of their node sampling method, which integrates feature-level and topological-level information. The results in Table 3 show that all 3 sampling methods utilizing additional information outperform random sampling, and the fusion of feature-level and topological-level information achieves the best performance. Furthermore, the authors investigate the effect of gradient norm scores on the performance of FTF-ER. They compare their method with variance using random scores, mean of feature scores, and coverage maximization scores to calculate the feature-level importance of nodes. The results in Table 4 show that their original method achieves the best performance in both average accuracy and average forgetting. The authors also provide a visualization of the evolution of average accuracy throughout the learning process on the task sequences of 4 datasets in Figure 4. The results show that FTF-ER exhibits performance close to the upper bound throughout the entire learning process on all 4 datasets, indicating its effectiveness in alleviating catastrophic forgetting issues. Overall, the authors demonstrate the effectiveness of their proposed method, FTF-ER, for continual graph learning, and provide insights into the importance of integrating feature-level and topological-level information for node sampling. In class-incremental learning, CIL, tasks, catastrophic forgetting remains a significant challenge, where a model's performance on previous classes degrades as it learns new classes. To alleviate this issue, the proposed feature and topological fusion-based episodic memory, FTF-ER, method integrates Hodge decomposition on graphs to compute the topological importance of nodes, fusing feature and topological information. This complementary approach fully leverages comprehensive graph data by assigning a score to each node based on its topological significance. This score, combined with the feature information, generates a fusion matrix used for selecting informative samples and computing weights for updating the model. Experimental evaluations on 4 diverse datasets, Amazon Computers, Quorafool, OGB-Arxiv, and Reddit, demonstrate FTF-ER's state-of-the-art performance in CIL tasks, surpassing existing methods in terms of accuracy and efficiency. Moreover, FTF-ER exhibits comparable buffer storage costs to topology-agnostic methods. Visualizations of the performance matrices for FTF-ER across datasets provide further insights into the effectiveness of this method in alleviating catastrophic forgetting issues. By merging feature and topological information through Hodge decomposition, FTF-ER showcases the benefits of considering the inherent graph structure in class-incremental learning. I'm happy to help. However, it seems that you didn't provide the content to refine. Please paste the transcript you'd like me to refine, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration, following the guidelines you provided. The Hodge decomposition theorem, a fundamental concept in mathematics and physics, states that on a compact and oriented Riemannian manifold, any differential form can be uniquely decomposed into 3 components: an exact form, a coexact form, and a harmonic form. This decomposition allows for the categorization of differential forms into 3 distinct types, each with its own physical interpretation. The Hodge Laplace operator plays a crucial role in this decomposition, enabling the distinction between exact forms, coexact forms, and harmonic forms. These types of forms are used to describe potential energies, circulation phenomena, and states of equilibrium or scenarios devoid of sources, respectively. In extending the Hodge decomposition theorem from its manifold version to graphs, several key concepts are defined, including d, delta, and delta when k equals 0. The Hodge Potential Score, denoted as omega 0, g, s, v right pointing arrow r, is introduced to understand the behavior of fields in the absence of external influences. This paper provides a comprehensive overview of the Hodge decomposition theorem and its applications in different areas of mathematics and physics, particularly in the context of differential forms and Riemannian geometry. It highlights the significance of the Hodge decomposition theorem in understanding the properties and behaviors of differential forms and its implications for various fields of study. Graph theory and Hodge decomposition are fundamental concepts in analyzing graph-structured data. Edge flows, denoted as omega 1, g, are functions that map edges to real numbers, as defined in definition C4. The gradient operator, grad, maps functions from omega 0, g, to omega 1, g, computing the difference between function values at adjacent nodes, as per definition C5. Conversely, the negative divergence operator, div, maps functions from omega 1, g, to omega 0, g, calculating the sum of function values at adjacent edges, as introduced in definition C6. The graph Laplacian operator, delta 0, is defined as the composition of the divergence and gradient operators, delta 0 d0 div grad. This operator computes the difference between function values at adjacent nodes and the sum of function values at adjacent edges. The Hodge decomposition theorem on graphs, stated for the case where k equals 0, decomposes a graph signal into 3 orthogonal components. The gradient component, the curl component, and the harmonic component. The gradient component represents the conservative or curl-free part of the graph signal, expressible as the gradient of a potential function defined on the nodes of the graph. The curl component represents the rotational or divergence-free part of the graph signal, expressible as the curl of a potential function defined on the edges of the graph. The harmonic component is the part of the graph signal that is both gradient-free and divergence-free. These three components form a complete and orthogonal decomposition of the graph signal, providing a way to analyze and understand the different aspects of the signal's behavior on the graph. The Hodge decomposition theorem on graphs is generalized for the case where k element of n, decomposing a graph signal into three orthogonal components: the gradient component, the curl component, and the harmonic component. The gradient component captures the conservative part of the signal, the curl component captures the rotational part, and the harmonic component captures the part that is neither conservative nor rotational. The proof that delta 0 corresponds to the usual graph Laplacian operator is provided, showing that the graph Laplacian operator can be expressed as the sum of the degrees of adjacent nodes. This operator is used to compute the difference between function values at adjacent nodes and the sum of function values at adjacent edges. The definitions and theorems presented in this section provide a mathematical framework for analyzing and understanding graph-structured data, with the Hodge decomposition theorem on graphs being particularly useful in applications involving signal processing, data analysis, and machine learning on graph-structured data. The influence of hyperparameter beta on average accuracy is investigated across 4 datasets: Amazon Computers, Quorafool, OGB-Arxiv, and Reddit. Figure 6 illustrates the distinct effects of beta on different datasets, with a 14% performance fluctuation observed on Amazon Computers and a mere 0.8% fluctuation on Quorafool. Notably, the peak consistently occurs at the middle position on all datasets, corroborating the effectiveness of the feature-topology fusion sampling. Implementation details of the experiments are provided, including the utilization of the Atom Optimizer, an initial learning rate of 0.01, 200 training epochs, and regularizer hyperparameter settings of 0.1 and 0.5 for L1 and L2 regularization, respectively. The buffer size for each class is set to 60, 60, 400, and 100 for Amazon Computers, Quorafool, OGB-Arxiv, and Reddit, respectively. The backbone structure is uniformly set as a 2-layer network with a hidden layer dimension of 256 for fairness. A qualitative analysis is conducted on the Amazon Computers dataset to demonstrate the efficacy of node representations learned by FTF-ER. Figure 7 presents the 2D TSNE projections of embeddings in 4 models, where nodes with different labels are represented by dots in distinct colors. The results show that FTF-ER exhibits a clearer separation of nodes from distinct communities compared to alternative methods, capturing distinctions among nodes within diverse communities through the gathered node information. Furthermore, the paper derives the equation for delta 0, regarded as the graph Laplacian dA, and examines the sensitivity of the hyperparameter beta on average accuracy. This analysis highlights the significance of beta in modulating the performance of FTF-ER and underscores the importance of careful hyperparameter tuning.